In this lecture, we'll be looking at indeterminate forms, and in particular, we will be racing functions against each other. Recall L'Hopital's rule. If you have differentiable functions f and g, and you're looking at the limit as x goes to a of f of x over g of x, and direct evaluation of this expression yields an indeterminate form of 0 over 0 or infinity over infinity, we can use L'Hopital's rule with the limit of the quotient being equal to the limit of the quotient of the derivatives. We're going to use this now in the context of racing functions against one another. This becomes very handy when we study the topics of convergence of sequences and series. So the issue of how functions race against one another as, say, x goes to infinity will matter, and the three functions that we will race against one another now, round robin style, will be polynomials, exponentials, and logarithms. And if you think about the graphs of these, as we've learned previously, if you have, say, a logarithm, so y equals a natural log of x, we know we get something that looks like this. For a polynomial, say something like y equals x squared, we know we get something like this. And again, our concern here is about the behavior as x goes to infinity. So we don't worry about anything going on to the left of the y-axis. And we also have our exponential. So say y equals e to the x. And the question becomes, how do these outpace each other? As x is going to infinity, how much faster is the exponential going to infinity than, say, a polynomial or a natural log? So let's take a look at this round robin tournament. And so the first pair that we will race will be the exponential versus the log. And from the graph we just looked at, we know direct evaluation tells us both the numerator and the denominator are approaching infinity. And so that is an indeterminate form that allows us to use L'Hopital's rule. And so the limit of that quotient is the limit of the quotient of its derivatives of the numerator and the denominator. So the derivative of e to the x with respect to x is e to the x. The derivative of natural log of x with respect to x is 1 over x. This becomes the limit as x goes to infinity of x e to the x. You have a product of two terms that are both going to infinity. So this is going to infinity. And this means, if we look at these two functions, which of course are inverses of one another, what this means, this infinite limit, is that the numerator on its trek to infinity is dramatically outpacing the denominator on its track to infinity as we move down the positive x-axis. So you can think of this as a race where it's no contest. And an example I like to think of is the classic Bugs Bunny cartoon where Bugs Bunny is racing the tortoise. And when they say go, Bugs Bunny basically disappears because he's so much quicker than the tortoise. He's in order or orders of magnitude faster than the tortoise. And that's what this is telling us. Again, the race is that e to the x going to infinity, natural log of x going to infinity. By taking the limit as x goes to infinity here, we get a sense of which one is going to infinity faster. This limit of this quotient being infinite means e to the x is infinitely outpacing natural log x in the trek to infinity. So that's our first of these, and so this means the exponential wins. Then let's pair the exponential and the polynomial. Again, we know the numerator is approaching infinity, as is the denominator. And so we can use L'Hopital's rule to say this is the limit as x goes to infinity. Derivative of e to the x with respect to x is e to the x. Derivative of x squared with respect to x is 2x. But note, if we directly evaluate again, both numerator and denominator are approaching infinity. So we can do another round of L'Hopital's rule to get the limit as x goes to infinity of derivative of e to the x is e to the x. Derivative of 2x is 2. And we now know that that's infinity. So when we're looking at these graphs, y equals x squared, and say y equals e to the x, on this scale it's not as clear. But we know from this result, both are racing to infinity as x goes to infinity. But this result tells us that the exponential is dramatically outpacing the polynomial. And you can see it wouldn't matter what degree this polynomial is. If it was a cubic polynomial, you would just have another round of L'Hopital's rule. If it was to the 100th degree, you'd have 100 rounds of L'Hopital's rule and still get that the exponential wins. So we see again here that the exponential wins. The exponential is dramatically outpacing the polynomial. So the exponential is our winner. Now we need to run the two losers against one another, namely the polynomial versus the log. And again, we know x squared is approaching infinity, as is the natural log of x. So L'Hopital's rule tells us this is the limit as x goes to infinity. The derivative of the numerator is 2x. The derivative of the denominator is 1 over x. Simplifying, we get the limit as x goes to infinity of 2x squared, which is infinite. And so now we see that our polynomial y equals x squared beats natural log of x in this major way. Again, it's the pace at which x squared is going to infinity dramatically outpaces the pace at which natural log of x is going to infinity as we go to the right as x approaches infinity. And so this gives us our hierarchy. So as x goes to infinity, we know exponentials are the fastest, and those outpace x squared, which is our polynomial, which outpace logs. So fastest to slowest. And this is something, again, that will become very handy when we are studying the convergence of particularly infinite series. But this is a very nice use of L'Hopital's rule to be able to do these races.